In the last few lectures, we were examining forced convection, boundary layer theory in the limit of high Peclet number, and we had considered two specific cases which I will summarize here. First was the flow past a flat plate. This was a plate of section of length L. Okay. Okay, in which the velocity decreased to 0 at the surface, and we had used a coordinate system where x was in the flow direction, z was in the cross stream direction, and in the limit of high Peclet number, where convection is large compared to diffusion, we would expect the effect of the disturbance to the temperature due to the flux from the surface to be restricted to a thin region close to the surface. Okay. Recall that we had taken the wall temperature as Tw, the temperature in the fluid far from the wall as T infinity, and we had expressed a scale temperature T star is equal to T minus T infinity by Tw minus T infinity, in which case T star is equal to 1 at the surface and T star is equal to 0 far from the surface. And this will be a common procedure. We will define a scale temperature so that T star is equal to 1 at the surface and T star is equal to 0 far from the surface. The length was scaled, the cross stream distance was scaled by a boundary layer thickness. Okay. We defined a similarity variable as z by delta x, which is a function of x. The boundary layer thickness is a function of x. The rationale was at a given location x, location x from the start of the heating section, the temperature at the point x depends only upon the distance from the upstream end of the heating section, not on the total length L. Okay. And the reason is because in the limit of high Peclet number, we can neglect streamwise diffusion in comparison to cross stream diffusion. Convection transports heat downstream, and diffusion is perpendicular to the flow direction, and therefore there can the total length cannot affect the temperature field at a location that is upstream of the end of the heated plate. And because of that, the local temperature depends only upon the boundary layer thickness, which is a function of x from the start of the heating section. And we had substituted these two into the equation Vx partial t by partial x is equal to alpha times partial square t by partial z square. Substituted for x and z in terms of the similarity variable, and for the velocity we had assumed that the velocity close to the surface, okay, the velocity close to the surface is actually a linear function of distance from the surface. Okay. So, even though the velocity has a curvature close to the surface, we can assume a linear function of distance from the surface. Okay. That is Vx is equal to Vs prime times z, where Vs prime is the strain rate at the surface. Okay. Okay, at the surface. Okay. Based upon these, we had got solutions for the boundary layer thickness and for the temperature field. Okay. The temperature field, the equation for the temperature field was minus eta square dt by d eta is equal to d square t by d eta square. This subject to the boundary conditions T star is equal to 0 as eta goes to infinity. Okay. T star is equal to 0 for eta going to infinity, and T star is equal to 1 at eta equals 0. Subject to these two boundary conditions, I got a solution for the temperature field T star is equal to 1 minus that was the solution for the temperature field. Okay. And the solution for the heat flux at the surface was Qz at z is equal to 0 is equal to minus k into T w minus T infinity by delta x, okay, temperature gradient, okay, times the value of the temperature gradient at dT star by d eta at eta equals 0. Okay. And if you recall, this I had shown you this the value of this temperature gradient at the surface was calculated from the equation for the temperature that I had. Okay. And from that I got the heat flux as minus k into Tw minus T infinity by delta x into, there is a plus sign, into minus 3 power 2 by 3 by gamma of 1/3. Okay, so that was the final solution for the temperature field in terms of the variable eta. Okay. Okay, in terms of the variable eta, okay, I had got the solution for the temperature field, and from that the heat flux. The equation for the boundary layer thickness was also solved, and the final temperature I got for the boundary layer thickness was delta x is equal to 3 alpha x by Vs prime whole power 1/3. Okay, this was the first order differential equation for the boundary layer thickness, which we had solved in order to get the solution. And I had substituted this solution into the heat flux at the surface. Okay. So, you substitute this solution into the expression for the heat flux at the surface. Okay. This will give us delta x is Qz okay, is equal to k into Tw minus T infinity by 3 alpha x by Vs prime whole power 1/3, okay, into 3 power 2 by 3 by gamma of 1 by 3. Okay. That was the solution for the heat flux at a given location x. Okay. To find out the average heat flux, we have to integrate this over the entire length of the plate. Okay. Qz, Q average 1 by L integral 0 to x 0 to L dx into k into Tw minus T infinity and this we had simplified, if you recall, in a few lectures ago, and we had got this as k into Tw minus T infinity by L, okay, into Vs prime L square by alpha, okay, into 3 power 4 by 3 by 2 gamma of 1 by 3, okay, some coefficients, okay, and that was the expression. Now, from this expression we can get the heat flux, the Nusselt number correlation, okay, because the Nusselt number is equal to Q average by k into Tw minus T infinity by L, because the scaling for the length in this case is the length of the plate for the flow past a flat plate. Okay. And this we had got it as 0.81. Okay. 0.81 comes from these constants over here. Okay. If you evaluate these constants, you get a value of about 0.81 into Vs sorry, there should be a factor of 1/3 here. Okay. Okay, so, it is basically the Peclet number based upon Vs prime and L to the power of 1/3. Okay, so, that is the expression for the correlation for the Peclet number. We had done this the same thing for a pipe flow, okay, for a parabolic profile. Wherein there is a heated section of the pipe which starts at x is equal to 0. Okay. And before that the temperature is T is equal to T infinity and T is equal to Tw in this heated section. Okay. And T is equal to T infinity in the bulk of the fluid. In this case as well, you would expect the diffusion from the surface to be confined to a thin boundary layer near the surface, and the boundary layer analysis can be used only when the boundary layer thickness is much smaller than the radius of the pipe. Okay. If the boundary layer thickness is much smaller than the radius of the pipe, you can consider this to be the same as the flow past a flat plate. Okay. You can consider this to be the same as the flow past a flat plate, because the radius of curvature is much larger than the thickness of the boundary layer close to the surface. Okay. And once you do that, the expression for the boundary layer thickness is the same as that for the flow past a flat plate. Okay. 3 alpha x by Vs prime whole power 1/3. Okay. In this case, the strain rate at the wall was derived earlier. Okay. So, in this case the strain rate at the wall Vs prime was determined in terms of the average velocity as Vs prime is equal to 8 times V average by T. So, the boundary layer thickness is 3 alpha x by 8 Vs prime by D, okay, whole power 1/3. Or I can write it as 3 alpha d x by 8 Vs prime whole power 1/3, okay, where D is the diameter of the pipe. Okay. The boundary layer thickness will be small compared to the pipe radius, okay, only for delta x by pipe radius d by 2 very much less than 1. Okay. Okay. And this reduced to, okay, 3 alpha L by 8 V average d square power 1/3 very much less than 1, okay, or L by d much smaller than V average d by alpha, okay, okay, which is the Peclet number. Okay. And there was a factor of 3 there, so I should put in the factor of 3 there. Factor of 3 is not really important, but okay, it was there in the original expression, so I am putting that in. Okay. So, that is the condition under which the boundary layer thickness is much smaller than the pipe radius. Okay. Under this condition, I can get the average flux, okay, at z is equal to 0, where z is the distance from the pipe wall, okay, where z is the distance from the pipe wall. This is equal to minus k into Tw minus T infinity, okay, by 3 alpha d x by V average whole power 1/3, okay, times 3 power 2 by 3 by gamma of 1/3. Okay. So, that is the flux at a given location x. I can get the average flux, okay, q average is equal to 1 by L integral 0 q z at z is equal to 0. Okay. So, that is the average flux. Okay. And then the Nusselt number is given by my apologies here, the strain rate I should put as 8 times VAV, okay, because the strain rate is 8 VAV by D here. Okay. I got it as the strain rate finally once I took the average flux and then defined the Nusselt number as Q average by K T W minus T infinity by D. Okay. This gave me 1.62 into V average D by alpha power 1/3 D by L power 1/3. Okay. That is the correlation for the Nusselt number. Okay. Using the same procedure, integrate the flux. Okay. The flux is proportional to x power minus 1/3. So, I will get 3 by 2 times x power 2/3 in the expression for the flux. Substitute that in and divide by k into T w minus T infinity by D, and I get the Nusselt number correlation. Okay. And I had also solved this for you for a power law fluid. The only thing that changes there is this one. Okay. The only thing that changes there is this. Okay. For a power law fluid, you recall that we had got V s prime is equal to 2 into 3n plus 1 V average by n d. Okay. So, instead of this 8 here, I have 2 into 3n plus 1 by n d substituted in this equation, and you get the Nusselt number correlation for the flow in of a power law fluid in a pipe. Okay. So, that is okay. So, now we will start looking at a slightly more complicated example, and that complicated example is the flow around a spherical particle. Okay. Okay. So, we have a sphere of radius r, okay, with temperature at the wall T is equal to T naught at the surface and T is equal to T infinity far away, okay, in a velocity field with free stream velocity Vfs far from the particle. Okay. And we would like to find out what is the Nusselt number correlation for this case. It is most convenient to use a coordinate system in which the axis, the axis of the coordinate, which I will call x here, is aligned along the flow direction. In this case, opposite to the flow direction. A spherical coordinate system, because the problem is axisymmetric around this axis. You have a sphere and which is isotropic, it has no direction. The flow velocity has only one direction. That means that if the axis is aligned along the flow velocity, the velocity field and the temperature field should be independent of the angle around this axis. So, I can use a spherical coordinate system where r is the distance from the origin and theta is the azimuthal angle from the axis, which is aligned in the direction opposite to the flow. So, that is the problem. And we consider this for high Peclet number. Peclet number, I will define it as V free stream into diameter by alpha. That is the Peclet number definition. In this case, the free stream velocity times the diameter divided by the thermal diffusivity. Okay. So, there is flow past the surface and there is convection due to the flow and there is diffusion of heat from the surface, and because we are in the limit of high Peclet number, the heat that is diffusing from the surface perpendicular to the surface is rapidly convected downstream due to the flow under high Peclet number conditions. Okay. Therefore, it will be restricted to a thin region close to the surface. Okay. You would expect the disturbance to the temperature field to be restricted to a thin region close to the surface. Okay. And this flow field, it goes around the sphere. Okay. So, it goes it goes symmetrically around the sphere, and along the axis where the axis intersects with the surface, okay, there are 2 points. Okay. These are called the upstream and the downstream stagnation points. Okay. Okay. Okay, these are called the upstream and the downstream stagnation points, okay, which are points of symmetry on the surface through which the axis passes, okay, on the surface, and these will become important in our later discussion. Okay. And so, based upon this, we have to find out what is the heat transfer rate, the average flux, and thereby the Nusselt number correlation for a specified velocity field for the flow around this particle. Okay. And the specified velocity field is, okay, this is given, okay, this is given to you. We can obtain this velocity field by solving the Navier-Stokes equations in the limit of low Reynolds number for a laminar flow. Okay. But that is outside the scope of this course. So, for the present, we will just assume that these velocities are given. Okay. Vr is equal to the velocity in the radial direction minus cos theta 1 minus 3 r by 2 r plus r cubed by 2 r cubed. Okay. That is the analytical solution for the velocity field in the radial direction. Okay. And the azimuthal velocity is going to be equal to sin theta into 1 minus 3 r by 4 r minus r cubed by 4 r cubed. Okay. That is the known velocity field. Okay. And the conservation equation for the temperature is Vr partial T by partial r plus V theta by r partial T by partial theta, okay, is equal to alpha into the Laplacian in the spherical coordinate system. Okay, so, that is the equation. Okay. Scaling T star is equal to T minus T infinity by T 0 minus T infinity, okay, which means that T star is 1 at the surface and 0 far from the surface. Okay. R star is equal to R by R. Okay. And the velocities we will scale as Vr star is equal to Vr by V free stream, okay, and V theta star is equal to V theta by V free stream. Okay. So, those are the r and the theta velocities. Okay. Substitute that into the conservation equation, okay, and you will get a factor of V free stream into R by V. Note that we do not have to scale theta because it is an angle, okay. It is already dimensionless. Okay. On the right side I will have alpha by R square. Okay. Note that in this particular direction, as the fluid is flowing around the particle, okay, as the fluid is flowing around the particle, the theta direction is the streamwise direction in this case. The direction of increasing theta is the streamwise direction in this case. Okay. So, now you can see that the velocities here, okay, the expressions for the velocity here, okay, they are slightly complicated, okay. And it's obvious that if we substitute these velocities into the conservation equation, it is going to be too technically difficult to solve them analytically. Okay. However, we do not need the expression for the velocity everywhere in the flow. We only need the expression for the velocity close to the surface, because we know that the boundary layer thickness is much smaller than the radius of the sphere, and the velocity fields vary over a distance comparable to the radius. Okay. So, we focus attention on a thin region close to the surface. Okay. And in this region we have a surface and we have flow past the surface. Okay. We have flow past the surface. This flow is in both directions, the r direction and the theta direction. Okay. And it is sufficient to find out the velocity in this region. Okay. Okay. So, we will define a scaled coordinate, okay, just as we had defined a scaled coordinate for the flow past a flat plate as z, the distance z divided by delta, where delta is a boundary layer thickness. In that case, the boundary layer thickness delta was a function of x. In this case, the streamwise coordinate is theta. Okay. So, the boundary layer thickness will be a function of theta. Okay. Therefore, we will define the radius r star close to the surface. At the surface, r star is 1 because it has been scaled by the radius. Okay. So, close to the surface, r star is written as 1 plus a scaled variable times delta star of theta. Okay. So, delta star is the boundary layer thickness. Okay. Is the boundary layer thickness, it is a function of theta and it becomes smaller and smaller as the Peclet number increases, because the strength of the convection increases and therefore, the temperature, the heat flux from the surface is swept rapidly downstream and it gets confined to a thinner and thinner region as the Peclet number increases. And eta is the scaled coordinate in this cross stream direction that remains finite in the limit as the Peclet number goes to infinity. Okay. Therefore, this is basically a definition of eta as the distance from the surface, scaled distance from the surface divided by delta of theta. Okay. The scaled distance from the surface divided by the boundary layer thickness is the similarity variable eta. And we will express all quantities in terms of the similarity variable eta. Okay. So, first thing, we can reduce the complexity of the velocities by expressing them in terms of eta. Okay. So, how do I do this? I know that Vr star, okay, divided by the free stream velocity is 1 minus 3 by 2 r star plus 1 by 2 r star cubed. Okay. Express this in terms of eta. Okay. This is equal to 1 minus 3 by 2 into 1 plus delta star eta plus 1 by 2 into whole cubed. Okay. And since we are interested in only the leading order solution in an expansion in delta, I can use the expansion. Okay. 1 plus delta eta whole power, okay, delta star eta whole power minus n. Okay. Minus n is 1 for the first term, for the second term, and n is equal to 3 for the third term. Okay. This is equal to 1 minus n delta eta, okay, plus n into n plus 1 by 2 delta eta the whole square plus etc. That is the expansion. Okay. Therefore, Vr star, if I calculate 3 by 2 into 1 plus delta eta power minus 1 will be 1 minus delta star eta plus, okay, n into n plus 1 by 2. N is equal to 1 for this term here. Okay. So, n is equal to 1 for this term here. N into n plus 1 by 2 is just equal to 1. Okay. Okay. Minus 1 by 2. Okay. 1 minus n is 3 in this case, 3 delta star eta, n into n plus 1 by 2, n is 3. So, I get 3 into 4 by 2, okay, 3 4s are 12 by 2, that is 6 delta star eta the whole square. Okay. In this you can easily verify. Okay. So, okay, I've left out a cos theta there, so I should put that. Okay. You can see that this minus 3 by 2, okay, this was a plus, okay, so, okay, plus 1 by 2 and 1 will cancel out. Okay. I have a minus 3 by 2 delta eta and a plus 3 by 2 delta eta. So, these will also cancel out, okay, and I will get minus 3 by 2 delta eta square and plus 6 by 2 delta eta square. So, I will get plus 3 by 2 delta star eta the whole square. Okay. Similarly, you can do this for V theta. The same calculation, this will give you sin theta into 3 by 2 delta star eta. Okay. Okay. So, this is the simplification for the velocity very close to the surface. Okay. Now, we have to put this into the conservation equation and then solve it. This I will continue in the next lecture. I will see you then.